All right, class, what I'm going to do is go through the homework problems. I'm going to tell you this type of problem is standard. To expect these types, this class of problems. We'll go through them all. The first one was a difference equation. I'm going to bring some properties into view. Now remember, the properties are basically the same as the Fourier transform properties. The discrete time Fourier transform has basically the same property line. But if you look in the page of the book where the properties are, you'll see how these things are just applied to this to get all the information. The first problem was a difference equation. This is the most basic type of thing. It has y of n, right, minus y of n minus 1 equal to x of n, I believe. Is that right, class? What? A half in front of here?
Yeah.
All right, 1/2. Really, this is just a first order difference. We're going to see we're going to be using much higher order difference equations, and they will be at times. It requires some more expertise than what I'm about to show you here. Now we're going to do a transform of this. So first, we're going to assume that y of n will be transformed into y of capital omega. That's an assumption. All right? When you take the dtft of anything, it'll go into the capital omega domain. Before, if it was y of t, it would go into the small omega domain. That's how we distinguish them. Next, there's a property, and I think you know this, y of, really, you remember y of t minus a in continuous time just went to e to the minus j omega a times y of small omega. Do y'all remember that property, class?
Yeah.
Identical here, only instead of t, instead of a, now it's going to be n instead of t, it's n, instead of a, it's whatever the delay is. So here, we're going to have y of, and this is n minus 1, right? That will go to simply e to the minus j1, which is just 1, times capital omega times y of omega. Does everybody follow me on that? Give me a show of hands here. Let me see this. It's a simple property, but you have to know it. And x of n just goes to x of omega. So here, we can say clearly that this means that this function will become y of capital omega minus 1/2, right, times e to the minus j omega times y of capital omega, and this will be x of omega. Everybody agree with that? Should be no problem seeing this, right? Now the next thing we have to do is get a transfer function, output to input. Can you see? You're scrunching your face. Can you all see it? All right, good. When I do this, I'm going to say my h of capital omega is equal to y of omega over x of omega. Output over input, always that way, transfer function. Here, when I do that, I factor y of omega out of here, so I have 1 minus 1/2 e to the minus j omega, and this is going to be 1 over 1 minus e, or 1/2, pardon me, 1/2 e to the minus j omega. And that would be h of omega. Does everybody see that? All right, are there any questions about what I did so far? This is going to follow methodically. Now, I don't know if I asked this, but I should have. Did I ask for the impulse response?
You said y omega in terms of x omega.
All right, well that's it. Now, normally the next thing you do, so we're gonna go ahead and flesh out everything that can happen. We're gonna look for the impulse response. So if the input was an impulse, what would be the output? Well, the output would be h of n, correct?
You could ask for the impulse response.
What's that?
It's part one of it. It gives us an impulse input, and as for the
There's an A and a B. The A part is...
All right. Well, it's going to ask for h of n, isn't it?
Yeah.
All right, so part B is assume x of n is delta of n, is that right? And so we need the impulse response, which is h of n. Do y'all follow me, class? Give me a show of hands. All right. All right, so now to get that, this is one we looked up, and this is the one I put down. I think I put this down several times, but remember we figured out that a to the n, u of n, went to either 1 over 1 minus a e to the minus j omega, or as the book has it, e to the j omega over e to the j omega minus a. Either one of those is the same. I prefer the first one. The book likes this one. And I know why, because of some other things coming up. So for this one, that means the impulse response to this, h of n, would be simply equal to what? What is a for this one? Just look at the coefficient. Class?
1/2.
1/2, right. 1/2 and it's going to be to the n power u of n. You all follow me? How many say this? All right, we're going to move on to the next one. Next problem, 2. What does it say?
It's delta of n minus n naught.
Delta, these are the just straight, these are just things you should know. You shouldn't be able to need a table. You shouldn't even have to think about this. When I ask for delta of n, let me put this up here. You have to know this, that x of capital omega, unlike the continuous time Fourier transform, this is a sum, and the sum goes from n equals minus infinity to infinity of x of n, whatever that may be, times e to the minus j and omega. And remember, it repeats itself every 2 pi. Usually you say from minus pi to pi, you get some shape. Cut that out and just start stepping and repeating it every 2 pi. Now, when we look at this for delta of n, what do you know you're going to get as the transform of this? Pick one. It's 1. What has it been forever? You know, it's been that way with Laplace, with continuous time Fourier. It's always 1, right? Which is nice. Next, it's a time delay. Delta of n minus, is it n naught?
Yes.
All right, what do you know happens? Delay in time is what in frequency? Phase, right? Always a phase. And this will be simply e, right, to the minus j n naught omega. That's it, right? Now, well, I'll leave it at that. I want to say one other thing with the delta function. It's 1, right? But what's the one thing I didn't put down? I assume you know it. Every 2 pi it's 1, right? So it's 1 at 0, correct? It's 1 at 2 pi, it's 1 at 4 pi. Do you all see what I'm saying here? I just didn't write it down, right? Simply because I'm not going to. This is the frequency domain. Remember, the frequency domain takes from minus pi to pi, cut that out, and just move it from 2 pi to 4 pi. Follow me? And there's always that 1 there when it's either 0 or 2 pi or 4 pi and so forth. What's the next one I guess for?
It's 4 to the n u of n.
All right.
Now, I guess you're supposed to plug that into the transfer function.
What?
That's how I interpreted it.
No, I think, we'll do that. We're just going to get them right now. All right, we can do it. But let's go. What is this going to be? 1 over 1 minus 3/4 e to the minus j omega. And what you asked is I'm not sure I intended that, but I didn't give any answers for this one. I want people to struggle with them. And if you looked on Wolfram Alpha, I think, I don't know about your other thing, that symbolic thing, you can see that Wolfram Alpha does have, I believe, the DTFT, and so does MATLAB, by the way. You can get the answers to this. Did anybody look at Wolfram Alpha? Were they there?
Or yeah, you can't be discreet.
Yeah.
They don't have DTFT? Well, MATLAB does. That I guarantee you. Anybody look at MATLAB? They'll give you this stuff, and that's the nice thing about MATLAB. It does have all, you have to put SYMS. You have, just look up doing symbolic transforms or anything symbolic of MATLAB, and go to YouTube and you'll see all sorts of stuff where people just go out of their way to explain it. So if these are inputs to this right here, how do you get the output? It's always what? Input in the omega domain times transfer function in the omega domain, right? That's it. So if we take 1 here, right, part A, right here, 1, well then h of n, this is the answer to this one right here. Correct, class? What about to this one? What happens?
Then it's 1/2 n minus n naught, and then u n minus n naught. Is that right?
This is going to be the input, right?
Yeah.
All right, now I'm glad I got everybody's attention here. Now, you'll notice, let me say this. No, you can literally take this function and multiply it by this function or by this function, and you have the output. You follow me, class? Everybody? You're just taking this times this. Is everybody okay with that? So if you did this, we'll do it for the second one. If I take, this is for part B here, if I take e to the minus j n omega, right, and I'm going to multiply it by this function, that would be 1/2, right? Right here?
Yeah.
All right. That's it, right? Now, that's h of omega. Y'all see, at this point, we could group, we could say this is going to be e to the minus j, and then you could say n plus 1 omega here over e to the, wait a second, I'm sorry about that, it would be e to the minus j n minus 1 omega e to the j omega minus 1/2. You could do it that way, you could do it a variety of ways. Do you all see that, class? Now, I'll tell you what, because actually you know the output is really going to be what? Just think about this before we go through it in verse.
Time shift.
If delta t gives me h of n, right? Or delta n gives me h of n, right? If I take n minus n naught, I just take n minus n naught and replace that right there. Do you all see that, class? Because it's a time invariant problem. How many see that? You would literally replace n by n minus n naught right there, and the u of n minus by n naught. That's it. That's the simplest way to do that. And this one, right? That's the transform of that, right? Now listen to this. I don't want to spend much time on this. If I take this transform right here times this transform, right? I have two fractions, don't I? Can't we do a partial fraction expansion on that and get the coefficients? I don't want to do that right now, but you all see what I'm talking about, class? Give me a show of hands if you do. Remember, we're going to do this in Z transforms. You remember, we didn't do partial fraction expansion with Fourier, right? We did that with Laplace, right? Even though basically we were doing the same transform operations, Laplace transforms make it easier because you have that S variable to work with. We didn't have the complex thing to work with. That's what I'm going to save the partial fraction expansion for Z transforms, which is akin to Laplace, all right? So I'm going to leave that one alone for now, and I want to get to the next bunch of stuff. This is really what I was hoping to get to before I get bogged down. All right, what's the next problem? Say it again. Give me the next one.
Oh, maybe, let's see, where's that?
H of n equals.
It's, find the, transfer function, and it gives you h of n is equal to 1/2 to the n.
H of n equals 1/2 to the, hold on, to the n, go ahead. Cosine?
Cosine pi n over 2. And then that's all the un.
All right, and here, I use modulation on this one, so I'm gonna do it. So it's gonna be straightforward. I know that if I have 1/2 to the n, right here, right, times u of n, I know that's gonna go to 1 over 1 minus 1/2 e to the minus j omega. Right there. Does everybody agree with that? I don't want to move too quickly, but make sure you see this.
Yeah.
You good with me? All right, I'm going to leave it that way. I'm not going to do it the other way. Now, if I have this, I know if I multiply by a cosine what happens, right? And let me just bring this down here to make sure everybody knows this. X of n times cosine of omega naught n, this is a property, will transform as 1/2 times x of omega plus omega naught plus x of omega minus omega naught. Now the reason I did this is to absolutely underscore that property of modulation. People forget that. This is the most important one. Sine is the same basic thing, only there's a j there and there's a minus sign. But this is the important one, the cosine operator. So when I take this and I look at this, I say really my x of n is this, correct? All right, so that means for this one, it will become what? The 1/2 you put out right away. And then you see this is my x of n, and now I have to add omega naught to it. What is omega naught?
I over 2.
Right. So now I'm going to take 1 over, right? And it's 1 minus 1/2 times e to the minus j quantity omega plus pi over 2. Plus 1 over 1 minus 1/2 e to the minus j omega minus pi over 2. All right? That's it. That's the transform. Correct, class? Show of hands here. The next part I'm going to show you is important. And I want to give myself a little more form. Now, I don't know if you did the reading in the book on this one or not, but I'm going to show you how it works.
That's wait, again. The minus will be reversed for the part.
What?
So the first pi half should be minus, the second one should be positive.
Well, see, it says omega plus omega naught, right?
Yeah.
All right, take
Cosine-
this omega, right? And you're going to add omega naught, which is pi over 2.
But cosine is exponential of the minus j pi over 2 plus exponential of minus j.
I didn't understand. You said that again?
If you convert cosine to Euler equation, right?
I'm not doing a cosine of Euler. What I'm doing is saying, this is the modulation theory. It says this, right?
Yes.
All right, so if you take that, if this is x of omega, right? So if I add omega naught to this, it would be omega plus omega naught, correct? That's what I did here. Right?
Yeah.
Now, all right, do you all agree with that, first of all? Give me a show of hands. Got that? All right, that's my h of omega, the transfer function. What's the next part he asked for? And this is important, what I'm about to say. He's going to give you an input of cosine of pi over 2n, isn't it? Or not? Never mind. X of n of cosine, right? Pi over 2n. Pi over 2 is omega naught. That's the. We're just trying to break that out front. You all see that, class? Now, here's something important. This I'm going to use Euler's on. I'm going to say this right here is equal to 1/2 times e to the j, and now it's pi over 2n plus e to the minus j pi over 2n. I'm just putting Euler's formula down there for a reason, and this is very important. Now, anytime you have an h of omega, that is a filter characteristic. But if you have a continuous frequency, and if you look at this, isn't e to the j pi over 2n only at one frequency? It's at positive, right? Pi over 2. How many see that? Here, this is at minus pi over 2. Do you agree with me? Now, anytime you have an exponential like that, write this down. I want to make sure it's written down. You have it in your notes. You'll put a star here. If you have anything that's at a given frequency, where you have e to the j omega naught n, and it's going into a filter that has a characteristic h of omega. All right, that means any omega coming in there, it's going to, but this is at a constant frequency. Then your output here, let me do you one better. Put an A here so you can get an amplitude. I'm not going to add a phase to it right now. I'm just going to put an amplitude. Now what happens is this. My output here, y of omega here, or really y of n. Let me put it to you that way. I'll make it in the end domain. Y of n. The only thing you do is take this, evaluate the value of h at omega naught, the frequency, then get the amplitude and the phase, and this is like one term in that discrete time Fourier series stuff where I turn it into a cosine waveform. If you remember back, and your output right there, y of n will be this. It will be a, and then it's going to be times magnitude of h of omega naught. So now you evaluate that filter at the value omega naught, you get a magnitude. Then it's going to be e to the j, and it will be omega naught n plus the phase of h of omega naught. Because remember, that filter can have a complex value. Do you all follow me? I'm going to apply it to this one. How many see what I'm saying here? Think back to when we did, remember when we did this, the Fourier series, discrete time Fourier series? What did we notice? That you could take x of n and turn it into a whole bunch of exponentials, right? But we could take those whole bunch of exponentials, we could turn them into a cosine as well, couldn't we, class? And then from there, we could say, if we wanted the output of something, it would just be the value of c of n magnitude 2 times the value of C of n magnitude times the magnitude of h of n omega naught times the cosine of omega, really, it's n omega naught t plus phase angle of C of n plus phase angle of the other thing, right? Here, we're not even bothering turning it into a cosine. I'm going to leave it as one single exponential. And I'm going to say this is what comes out. Follow me, class? Now here's the application. This is my input. Is it a constant frequency? Yes, at 2 constant frequencies, in fact, right? So what's my output going to be for this filter? And this is my filter h of omega. Well, my output, y of n, work with me on this one, right, is going to be what? 1/2 for sure. Do you agree with that?
Yeah.
So I'll leave the half out in front. Right? Got that out in front. And then I evaluate this first at this frequency, at plus omega naught. Now watch this. That means I get 1 minus 1/2, and here's why. When this, excuse me, I should evaluate it. Yeah, no, that's right. This goes to 0 when omega is minus omega naught, so, or minus pi over 2. Do you follow me in this class? Use this one first. Just follow me. Use that frequency, minus pi over 2. At minus pi over 2, this is going to be e to the 0 or 1, right? So I get 1 over 1 minus 1/2. Do you all see that, class? Give me a show of hands. What happens to the next part of that? Plus 1 over 1. What's this going to be?
1/2.
It's going to be just positive 1/2, right? It's going to be, because this will be what? Minus pi, correct, class? And minus pi is 180 degrees. E to the minus j pi is 1, is minus 1 with a minus sign is plus, so this is 1 plus 1/2. Do you all agree with that, class? All right, now what's that? That is the value of h, right? That's the first part. I'm going to have to get rid of this. What's the phase of that, by the way? You'll notice those are both real numbers. There is no phase difference. Do you all see that, class? So I have that, and then I take the value of the actual input, which is going to be 1/2 as well, and it's going to be times e to the minus j pi over 2 n plus, and then you'll take this one and stick it in there. You're going to get the exact same thing, right? You're going to get this, and you're going to get plus 1/2 times, and it's going to be 1 over 1 minus 1/2 plus 1 over 1 plus 1/2, right? And then it's going to be times 1/2 times e to the j pi over 2n. Now, listen to me carefully.
The second one you got should be, well, it's the same thing.
It's identical.
Yeah.
Everything's identical because these two things, these two frequencies, occur at the singularities of this argument, really when the arguments go to 0. Follow me on this, class?
Okay, so
Yep.
the magnitude of h omega naught, that's just plug in h omega and use omega naught.
You use omega equals omega naught, right?
Okay, and since there's no complex, we don't have to do magnitude stuff.
It's given. That's the nice thing about this one. It's strict real. All right, follow me now and work with me on this one. Look here. What do I actually have? Isn't this 2 here? Right, so that's 2. What is this?
3/2.
3/2, right? Times 1/2. I have 1, right?
It's
That's
2/3 actually,
I mean
sorry.
2/3, sorry, 2/3. I have what? 1 plus 1/3 or 4/3, don't I? Do you agree with me? What do I have here? 4/3 as well. Do you all see that? Isn't that 4/3 too? Class, give me a show of hands here. How many see that? So really what I have is this is 4/3 times 1/2 times e to the j pi over 2n plus e to the minus j pi over 2n. And what is this right here? That's the cosine. Now, I did it that way on purpose to make sure you understand that you can put the individual frequency, the omega naught, into this filter, analyze the magnitude and phase, and then get the output here by taking this A times the magnitude of H at omega naught, and then adding e to the j omega naught n plus any phase change. Yes, sir?
How'd you get the other 1/2s?
Well, the idea, the whole thing about this is it's perfectly symmetric. When you look at this right here, you see you have a plus and minus pi over 2, right?
Yeah.
All right, when you look at the h of omega, you've got what? The actual argument's going to 0 plus or minus pi over 2, right? If you look at the magnitude of this, I mean the value of that at minus pi over 2, it's the same thing at pi over 2, isn't it? So it's 4/3 either way.
Well, I'm the second 1/2, because there's two 1/2. I was wondering the 1/2 next to the even minus.
See that 1/2?
I see that one.
All right, and the other one comes from here, x of n. Remember what Euler says? Cosine of pi over 2n is equal to 1/2 e to the j omega naught n plus e to the minus j omega naught n, right? That's where both of those halves come from. One's from the cosine, the other's from the transfer function. Okay, and you can look at this and it will be 4/3. Now there's another way to do this. You can simply put the cosine waveform in there. If you want to, you can put this cosine waveform in here and simply evaluate this at the positive frequency. You're going to get 4/3, and that will be the h of omega that you multiply it by. Do y'all follow me in that? You remember when we did this with the cosine waveform before? We had 2 times c of n times cosine of omega naught t plus phase angle of cn. How many remember that? That was your input? And your output was the same thing, except you also had to multiply by the magnitude of h of omega, right? N omega naught, pardon me, plus the phase angle you had to stick in there. How many remember doing that? You did a project on this, right? Make sure this is very clear in your minds, because this stuff, you're going to see a lot's coming at you in the next 3 weeks that minus spring break, 4 weeks, that has a lot to do with understanding this, and I'll spend a lot more time on that. Do you all see that, class? All right, next one. Tell you what, just to make sure everybody sees this, I'm going to do something a little different here. Let's see how you act for this. At this point, just to kind of flesh out the details, because I can see there's probably some uncertainty. See how you do on this one. All right, I'm going to let this be the transfer function of my system. Write this down. It's going to be 1/2, all right, times 1 over 1 minus 1/2 e to the j omega plus omega naught minus j, pardon me, omega plus omega naught plus 1 over 1 minus 1/2 times e to the minus j omega minus omega naught. And I'm going to let omega naught be simply pi over 2, or 90 degrees. Everybody got that? Same filter we had before, right? Identical. Do y'all agree? All right. Now, that's this is my filter, my h of omega. Now here, I'm going to put in x of n is equal to the sine of pi over 2n. And I want you to analyze that. You all see it's going to come in as a sine of pi over 2n, right? What did I do with the cosine? Just tell me.
Euler's first.
I used Euler's. So x of n would be what if I use Euler's? J over 2, there's a phase, right? Times what? E to the j pi over 2n minus j pi over 2, right? Isn't that right, class? Are you with me?
Yeah, it's doing the n of the even minus j pi over 2.
Couldn't hear you. What?
The n for even
Oh, n, thank you. And I'll break it and I'll go one step further. Just so you can see they're discrete terms. Do you agree with that? It's straightforward. There's nothing confusing about this. Straightforward Euler's. Now, what is j really? When I take a look at j, isn't that e to the j pi over 2? Y'all agree with that? Show of hands here, how many do? Pardon? Now, what happens if I have, follow me on this, j times e to the j pi over 2n? Isn't that e to the j pi over 2n plus pi over 2? Isn't that right? If I have j, and that's that, e to the j pi over 2. I forgot to shut this thing off. Sorry. Do y'all see what I did there, class? Here, let me do it this way. First, do y'all agree that e to the a times e to the b is e to the a plus b? You've got to agree there. Agreed? Now, that means if you have j times e to the j pi over 2n, you really have what? E to the j pi over 2 times e to the j pi over 2n, don't you? Add the exponentials, or the exponents, all right? Add the exponents. What do you get? You get e to the j, right? And then you have pi over 2, right? And you could just as well put n plus 1 there if you'd like, couldn't you? How many see that? Are you following me? If you have pi over 2 times n plus pi over 2, you can factor the pi over 2 out. All right, I'm just showing you different things. All right, getting back to this problem. This right here, my point is this can be written as e to the j, and it would be pi over 2n, right, plus pi over 2, and divided by 2, plus e to the minus j pi over 2, and this would be, that's a minus j, e to the minus j pi over 2n plus pi over 2 over 2. That's what I'm getting at. Y'all agree? What's the output going to be? Go ahead, take a look. Y'all agree with that? Be suspicious. Just add the exponents. Well, not yet. No, not yet. Sort of. Yeah, kind of, sort of.
Can you reread your?
I think I know what you're talking about. You want me to show you specifically how this becomes that, right? I'm going to do it up here for a reason. Just work with me with that one. If you give me x of n is equal to j over 2 times e to the j pi over 2n plus e to the minus j pi over 2n. You all give me that. All right, now what is j? E to the j pi over 2, right? So I'll go ahead and do it. That's e to the j pi over 2 times the first one is e to the j pi over 2n plus, and it's going to be e to the j pi over 2 times e to the, sorry, this is a minus. Somebody should have yelled at me right there. Yeah, that's a minus. Minus, right? Minus e to the j pi over 2 times minus j pi over 2n, right? Divided by 2. Do you all agree with that part? Agreed? All right, now add the exponents. First term is what? E to the j pi over 2n plus pi over 2. Just leave it like that, all right? So I've got the j there. Over 2. Do you agree with that? Right? We're adding exponents, that's it.
Why
Yes,
isn't
sir.
it j pi over 2 times n plus 1? Or that's the same thing.
If you take pi over 2 plus pi over 2 plus times n, right? It's pi over 2n plus pi over 2. Yes, sir. Go ahead.
Yeah, I don't know if you said it earlier, and I missed it, but what happens to J?
Well, here, you remember j is what? It's 1 at an angle of 90 degrees? Isn't that just e to the j pi over 2? Right? That's exponential notation. Y'all remember that from your circuits courses? You had to know that in order to pass, I think. All right, now, coming down here, you have what? E to the minus, e to the j, or minus j, pi over 2, n, right? minus pi over 2. I had a plus pi over 2, and it should be over 2. Now that's the input. Listen to me carefully. Please make sure you know how to do this, because you're going to get tested on this. Now, if I take this term in, right? It's at a frequency of pi over 2, right? Do you all see that? But it has a buried phase of pi over 2 as well in there. Do you all see that? So now we've got magnitude and phase. The magnitude is 1/2. Do you agree? Put just this term right here into this filter. What is my output going to be for that term? Just the first part. Y of n would be equal to the magnitude of 1/2, right? Times the magnitude of this, right? At what? At pi over 2. Correct, class? Remember last time we said the magnitude of that at pi over 2 is 4/3? How many do? Y'all remember that? We just put in what? Pi over 2 in here, and omega naught was pi over 2, and you're going to get 4/3. So now you get 4/3. If you don't know it, make sure you take a look at this. Then what's the next thing I do? Now I take my input, which is this first term, e to the j pi over 2n plus pi over 2, right? And what do I have to do? I've got the magnitude. I have to do one last thing. The phase, right? What's the phase of this? It was just 1. Or I mean, it's 0 degrees, isn't it, class? There wasn't an angle in there because it was at omega naught, which is pi over 2. Yes, sir.
Should the second term be pi over 2n plus pi over 2?
Yeah, it should be. I was thinking that. Because it's minus.
Because you factored out the negative.
You're right. That's fine. You're right. So this is the first term, and the second term is going to be plus what? Got to be the magnitude right here is 1/2, right? Then you evaluate this at omega is equal to, you got to take the magnitude of this, equal to minus pi over 2, which happens to be the same as the magnitude of plus pi over 2. Correct, class? So that's 4/3 again. And then you put down e to the j, or minus j, pardon me, pi over 2n plus pi over 2. And in fact, sorry, this is a minus. My bad. That's minus there. Wait. Yeah, there was a minus. I should have put a minus here. My bad. Well, wait. No, I take it back. No, it should have been a plus. I had minus j there. Minus j would be what? E to the minus j pi over 2, right? Let me just write this down. First, j is equal to e to the j pi over 2. Minus j is equal to e to the minus j pi over 2. Minus 1 is equal to e to the minus j pi. 1 is equal to e to the, really, j 2 pi. I'm just doing this to make sure everybody understands what I'm doing with the exponentials. You've seen this before, correct, class? How many have? Everybody has seen this, right? You've seen that anytime you have something, a at an angle theta, that is a times e to the j theta, right?
No.
Yeah.
I don't think I've ever seen that.
Did you have circuits?
I did.
Then you have seen it.
Okay.
Did you take circuits here?
Yeah.
Yes.
Who did you have?
Irwin.
You've seen it. I mean, Irwin lives in this arena.
You've seen like similar stuff?
No, this is phasor notation when you went to the constant frequency. How many remember phasors, right? Constant frequency. This is the whole basis of it.
He may have touched on it, but we never really used E as the base.
You don't use the E function.
You don't need to, because then you simply use the j omega portion, right? You suppress each of the j omega t. That's the whole basis for phasor analysis. When you do the phasor analysis, the thing is that each of the j omega t disintegrates from both sides of the equation, so you don't need to do it. It's at an assumed frequency. If you had it, look back on your notes. I mean, circuits is the thing that is the springboard into this right here. All right, do y'all see what I did there? I'm just trying to show you how you're going to get magnitude and phase, and you have to add both magnitude and phase to the functional forms. What's the next one?
It wants you to use the inverse DTFT for the
Yeah.
following. And it asks
Oh,
you
this is a good one.
And it gives you capital X omega is equal to omega, then it's pulse of pi.
Now, I want to tell you, this stuff right here almost guaranteed appears on the exams every time. This is the stuff that's so important because it uses duality. I'm just being honest with you that if duality is very, very important. You get at least one question, possibly two, on the first exam that have to do with duality because it's such an important theory. So if you look at this, I ask you for the inverse transform of this. I give you omega times p of pi omega, I think. Is that right? All right, this is my x of omega. Now please, class, hear me. When I say it's important, it's not just important, it's essential. You can lose 25% on an exam if you don't understand this very quickly. It's very easy to do. The examinations are tough to begin with, and if you have any uncertainty, it'll come out and usually just collapse. Trust me on this one. I have more kids bombing these exams because they have no real interest in this, and that's dangerous. You have to more or less throw in wholeheartedly in this. All right, now, right off the bat, what I'm going to do is suggest you think about not the omega domain, but the small omega and t domain. And the first thing I'm going to ask you is, and I'm going to do it this way. I like to do it this way, but stay with you. If you had a p tau of t, do you know what the transform of that is? Show of hands, how many do? All right, I'm seeing less than 50% know that. By this time, it should be ingrained in you. It shouldn't even be a question. This one has a transform of tau times the sinc of omega tau over 2. Do you agree with that? That's the first thing. Now, after that, if I said I had t times p tau of t, how would you get the transform of that? And there's a property that should come to mind. It would be j times the derivative with respect to omega of x of omega, right? How many remember that? T times anything in time means if you know the transform of that anything in time in omega, you're going to take a derivative with respect to omega, but you're going to multiply it by j. So it would be j times the derivative with respect to omega of the sinc function, right? All right, now what's the derivative with respect to omega of the sinc function? Believe it or not, people, they fall on their face in this one. They just put a question mark sometimes. All right, think about it. Define what sinc is. Sinc of omega tau over 2 is equal to what? This is the sinc.
Sine omega tau over omega tau over 2.
That's right. Times over omega tau divided by 2, correct?
What happened to the tau that you had above?
What?
What happened to the tau that you had above?
I'm glad I got you in this class. Because I'm trying to get this thing done, and I dropped that term. Thank you so much. You're a godsend to me. Anyway, wait, matter of fact, let me do it this way. Yeah, yell at me if I make a mistake. I enjoy that. All right, now, over here, and you should have yelled at me again. I'm going to multiply top and bottom by 2, just for the heck of it. And then I'm going to divide the tau out in front. Why? Because that way my derivative is just on that. Agreed, class? Now if I take a derivative of this is my function, I'll call it f of omega. If I take a derivative of f of omega with respect to omega, it's a derivative of these two functions. The 2 over tau stays there, right? So I take a derivative of sine of omega tau over 2, right? And that's going to be what? Tau over 2, correct? Tau over 2. And then it's going to be times what? Cosine of omega tau over 2 divided by omega. Do you agree with that for the first term? Second term is what? Well, it's going to be minus, it'll be an omega squared here, and then it's just going to be times the sine, right, of omega tau over 2 here. Do you all agree with that? If you take it, remember, it's derivative of the first, which is derivative of sine is tau over 2, cosine of omega tau over 2, times the second, 1 over omega, plus the first, sine, divided by the derivative of the second. Derivative was 1 over omega, omega to the minus 1, which brings out a minus 1 over omega squared. How many see this right here? You can go ahead and be suspicious some more, but it's right. This time it's right. All right, now, if you go ahead and multiply through, it doesn't matter if you want to do this or not, but if we multiply through by tau and 2, well, this term goes away, right? And I have 2 over tau out front. You can put a 2 over tau here if you like. Agreed, class? Now I have that derivative, which is the derivative of that, and I have to multiply it by j tau here, and then I'll put it here times cosine of omega tau over 2 divided by omega. I'm going to show you one thing. I'm going to multiply it by omega and just put omega squared down here. Then it's minus 2 over tau times the sine of omega tau over 2 here. And that would be the transform of t p tau of t in general. Do you agree, class? Now, if tau over here, tau, we're going to use duality. I think most people know where I'm going with this. I'm going to say duality says this. It says that if I take this function over here, and I multiply it by 2 pi, right? And then I'm going to take, instead of t, it's minus omega, and then it's going to be times p tau of minus omega. This is the basis of duality. Over here, I have a j tau, right? And then it's going to be times, not omega, but t. So it's going to be t cosine of t tau over 2 minus 2 over tau times sine of t tau over 2 divided by t squared. And that's the relationship here to here. You all agree with me? This is just duality, correct? How many see this? Now I make the case. If this tau, right there, is associated with something between minus pi and pi or less, then I can say this is also true of the capital omega domain. How many remember me saying that? If you have the transform for the small omega domain from something x of small omega to x of t, right? And you see that it is identical to the actual signature or the actual capital x of capital omega, the same exact thing between minus pi and pi, and 0 outside there, then you can replace small omega with capital omega, and that's what I'm about to do. But I'm going to do one other thing. You see that minus sign here? I can't get rid of that, so I'm going to multiply both sides by a minus. That's the first thing. All right? And then I'm going to divide by 2 pi. To get rid of that, I still have the omega. Now, can I make this positive, class?
Yeah.
Why?
It's symmetric.
Symmetric. P of minus omega is the same thing as P of plus omega, correct? It's an even function, so let's get rid of that. Now, I make the assertion. If tau is limited to pi, to 2 pi, limited to 2 pi or less, then I can say that I can take capital omega here, and this works. Make capital omega there. And over here, now, instead of t, what do I do? Come on, n, right? Right? Instead of t, it becomes n, and it's obvious. So this is n, this is n, this becomes n, and this becomes n squared. And there you have it. And that, in fact, is the inverse DTFT using duality. Understand, class? How many understand that? Duality is such a powerful thing. I mean, do you guys understand this? It's very, very straightforward, very, very obvious if you use duality. And it's so important. Now, I did have one property. I had to use the derivative, or the multiplication by t brings out a derivative over here times j, right? That's the only property. There wasn't 2 or 3. Yes, sir?
Where'd you get the minus sign?
Remember there was a minus omega? Remember when you do duality, you take what? This function, you replace t with minus omega, right? There was a minus omega in front there, wasn't there?
Oh, okay.
Right, because there's a t that becomes minus omega. Are you with me on that? Give me a show of hands. What about the last one? We can just talk through it. I had what?
With the same thing with the
Pi,
shift.
omega minus pi.
Capital omega minus pi. Now, ask yourself, do you know the transform of p of tau of t over here? Answer is yes, it's up there on the board if you don't know it, right? That's like an x of t, isn't it? What happens when you get a delay? Let me just put this down here. Please write this down, class. This is important. if I get this, what happens when I have P tau of T minus some cap T? Class, tell me. It's just e to the what? Minus j omega cap T times tau times the sinc of omega tau over 2. Is it not, class? Right? Now, can't you use direct duality to get this in the frequency domain? How many see that? Right? You better, come on, you guys do. It's not that hard. All right. Make sure you keep up with this. Do that homework. Make sure you get it down. I'm going to give you some more, and I'm going to tell you what we're going to do after this. I'll give you some more homework, and this is going to be really using difference equations and getting the transfer function and getting the frequency response. But we're going to start touching on Z transforms, because that really opens the door to all sorts of analysis, easy analysis compared to what we're doing right now. All right, see you next time. I know spring breaks. Come on. Yes, sir.
Which one is tau? How many of those T's are tau?
What's that?
How many of those T's are tau? And how many of those
What did you say? Walk over here, I can't hear you. What? Well, taus are these symbols. That's tau. That's tau. That's tau. That's tau. This is T. This is T.
What about the negative J?
T's always on this side. Tau's on it.
What about the negative J omega? The negative J omega.
Negative J.
On the right side.
Oh, this is cap T. This is right here.
So that's the only cap.
Yeah, it's just a delay. I could have used A there.